Hi everyone, this is Dr. Bilal and in this video I will be talking about Schrödinger equation. The Schrödinger equation encapsulates all pertinent information about a quantum system. It serves as a comprehensive descriptor of the behavior of a solid. The ability to solve the Schrödinger equation empowers us with the means to ascertain all relevant details concerning the solid. In the context of our study, solids are comprised of nuclei that are positively charged particles and electrons that are negatively charged particles. The main components of Schrödinger equation are Hamiltonian, energy, and the wave function. I will explain each term one by one. The first important term is the Hamiltonian. The Hamiltonian that characterizes a system must encompass all potential interactions within that system. Each type of interaction is associated with a specific energy, and the determination of the Hamiltonian involves accounting for all these energies. The challenge lies in identifying and calculating the various interactions present in the system. In practical terms, the Hamiltonian can be quite extensive. For instance, in the case of a solid, the Hamiltonian involves a summation over the kinetic energy of each individual nucleus. Considering one mole of nuclei, this leads to an enormous number of terms, typically on the order of 10 raised to the power 23. A similar summation is conducted for the kinetic energies for all electrons, as well as for all interactions between the nuclei and electrons, and among the nuclei themselves. Consequently, the Hamiltonian comprises a multitude of terms. Despite its complexity, there is no inherent mystery in the Hamiltonian formulation. It is a straightforward representation that encapsulates the various energies associated with the interactions within the system. The second important term is the wave function. The wave function is the key component in the quantum mechanical description of a system. Understanding the wave function essentially provides a complete understanding of a solid. In quantum mechanics, the wave function is a variable quantity that mathematically characterizes the wave-like properties of a particle. The value of the wave function at a specific point in space and time is directly linked to the probability of finding the particle at that particle location and moment. The wave function is a function basically that operates in a high-dimensional starting domain. One crucial property of the wave function, especially pertinent to particles like electrons, is its antisymmetry under particle exchange. This antisymmetric nature is significant in describing the behavior of electrons within the system. The third important term is the energy, distinguished from the wave function by its nature as a measurable and observable property. The energy can be calculated for a solid by considering the solid in the beginning in its ground state, a state corresponding to 0 Kelvin temperature. Then we incrementally introduce some energy into the system until we achieve a complete separation into elementary particles. In this state, one nuclei and electron exist positioned at infinite distances from each other. To determine the total energy, we aggregate contributions from various sources. Each contribution corresponds to experimentally known quantities. For example, we can reference the heat capacity of most solids or the energy required to remove each successive electron from an atom. By summing these contributions specific to the system under consideration, we can ascertain the energy derived from the Schrödinger equation. This process allows us to bridge theoretical principles with experimentally established values. providing a comprehensive understanding of the system's energy characteristics. So, the Schrödinger equation is a fundamental equation in quantum mechanics, serves as a key tool for predicting and comprehending the properties of crystals. The Schrödinger equation describes the behavior of quantum systems, particularly the wave function of particles such as electrons within a given environment. In the case of crystals, where atoms are arranged in repeating pattern to form a lattice structure, the behavior of electrons within this lattice is crucial in determining the crystal's properties. By solving the Schrödinger equation for the electrons in the crystal, we can obtain the wave function, providing insights into the distribution of electron density and energy levels. This information in turn allows for predictions about various properties of crystal, including its electronic structure, electrical conductivity, optical behavior, and many more. In essence, the Schrödinger equation provides a theoretical framework that enables us to analyze and understand the quantum mechanical aspects of crystals, offering valuable insights into their observable properties and behavior. Thank you for watching this video.